Hey, welcome to the video. Let's do some math. We're going to talk about ellipses today. An ellipse is one of the conic sections. Kind of crucial to understanding what an ellipse is looking at the definition of it. So this is the geometric definition of an ellipse. It's a curve that is the locus of all points in the plane, the sum of whose distances from two fixed points, called the foci, is a given positive constant. Now, this really doesn't make a lot of sense. If you think of when you think of an ellipse, maybe the first thing that comes to mind is like a circle that's been stretched out. And that's exactly what an ellipse is. Essentially, it's a circle that has some eccentricity. And so this eccentricity is kind of what determines how stretched out a circle is, or sorry, how stretched out an ellipse is. We don't, in this class, this video is for pre-calc, we don't talk a lot about eccentricity. But we're going to introduce the letters and the labels that kind of like define that. Now, something that's confusing in this written definition is the word locus. In math, we use the word locus just to define like the set of all the points. So set and locus is kind of the same thing here. Now, what's tricky is that I don't have a good way to like show you physically what's happening with this. What I would do in class would be I'd put two suction cups on the whiteboard with a string hanging between the two of them. So the string's connected to both suction cups and there's some slack on that string. I'd put a marker in the string basically and try to draw a circle, or try to draw a curve around the suction cups. And in doing so, we'd produce an ellipse. I'm going to try to replicate that here on this graph. So we have a point, if we had a point right there, which is 4 over from the y-axis, and we go 4 over in the other direction from the x-axis, it doesn't really matter. But if I were to say, all right, this, let's use a color, let's use blue, that this point right here, that the distance from that red dot, okay, the distance from that red dot, so like this distance right here to that blue dot, and then this distance from that blue dot to the other red dot, the sum of these distances, like that's D1 and that's D2, the sum of those is constant for any point that is also on this curve. So for example, if I had like, so here, D1 plus D2 is a constant, okay? So if D1 plus D2 is a constant, that means if I had a point over here too, let's do a completely different looking point. Maybe let's do this point. Okay, if I had a point right here, now, like, gotta understand that these points are not going to be drawn really accurately because I don't have an ellipse in mind, but what it says is that this distance here, let's say this distance is D3 and this distance is D sub 4. D sub 3 plus D sub 4 would be equal to D sub 1 plus D sub 2, like for all locations. So let me see if I can kind of show you what that might look like again. So let's put those foci back. These red points are ultimately, they're going to be foci. And I'm going to try to draw in an ellipse. And this is not going to be the greatest ellipse ever drawn. Let's do, please know that I'm doing this on a computer, and so it's like hard to draw, so please don't judge me that much. Smooth this out a little bit. Okay, sure, this is pretty bad. Hold on, I'm just gonna make sure I get a good ellipse on this. Okay, so there's my ellipse, kind of. And I am, what I said previously was that if I took a point right there, or if I took a point like right there, that the distances, the sum of this distance plus this distance is the same as the sum of this distance plus this distance. And that's true for every single point on the curve, on the ellipse itself. Okay, so that's what that says. Uh-oh, that went away. I don't know how to put it back. Nope. This isn't going well so far. Alright, there we go. So that's a really terribly drawn ellipse. I wish I could do it better, but I just can't. And so that's what an ellipse is. I have to do better than this. I'm sorry. I'm gonna do kind of free-handed. I'm not gonna try to be as precise. Okay, here we go. Oh, it's bad. It's okay. We're gonna attempt it again. Yeah, that's a little better. Okay, can I erase this? Oh, alright, I'm gonna put that hot part back in. Okay, sure. Something like that. So here's what we're gonna do. We're gonna define a few things. So there are some distances here. First of all, we should probably define what is going on with the axes. So the longer axis, in this case it's the horizontal axis, the longer axis of an ellipse is called the major axis. Okay, the smaller axis of the ellipse is called the minor axis. Now, in this particular example, the major axis is horizontally oriented and the minor axis is vertically oriented. That's not the case always. Sometimes ellipses are vertically, like they're stretched more vertically. In that case, the longer of the two axes is still the major axis, and it would be the vertical axis. The major axis also contains, it always has the foci on it. In addition to having the foci on it, it has the vertices on it. So the vertices of an ellipse occur at the end points of the major axis, or they are on the major axis. So these are called vertices. I'm not going to write the other one over there, but this is a vertex. And well, I guess I will say there's a vertex here too. Okay. There's also something we can say is that this point here and this point here, these are called co-vertices. So they're called co-vertices. Okay, I'm not going to draw the other one. And so that's kind of definitions of what's going on there. And of course the red points, like we said, the red points, these are foci. Okay, so we got two of them inside this ellipse. The foci will always be on the inside of the ellipse. Okay, so I mentioned before there's something called eccentricity. The eccentricity has to do with how stretched out the ellipse is. And when we design elliptical things for like the real world, we care a lot about where those foci are. The foci, the distance between the center. Oh, we forgot to put the center. Yeah, the center of the ellipse, right there. That's the center, and it's HK. Okay, the center is at coordinates HK. We're used to that if we ever talked about vertices of parabolas or centers of circles or anything like that. So HK is the center of the ellipse. As mentioned, it matters a lot what this distance is, what the distance from the center to a focus is. And that distance is that we use a label for. It's actually C. Okay, we use a label C for the distance from the center, HK, to one of the foci. That distance obviously also is C in the other direction to the other focus. It's like the two foci are equidistant from the center. The distance between the two foci is 2C. Okay. We also care about how far it is from the center to a vertex. And so that distance there is A. The distance from the center to a vertex is A. And then the distance, or just let's say this, the distance horizontally from the center to either the vertex or the co-vertex is A. And then the last thing that we have, color can I use for this? Orange. That this distance here, vertically, this distance is called B. And so I need to come up with a relationship between A, B, and C here. And to do that, we can use the definition of an ellipse to come up with, and do some casework on different points, kind of come up with this. So what we're going to say is let's examine this point right here. Okay, at that point right there, when we talk about these distances, like the distance from there to there is that obviously they're the same. Like that's a triangle. It's a call that an isosceles triangle, and you have this side is equal to this side. Okay, and then we can call this letter, we can call this like H, okay? So what we're gonna do here is say that at that point, at that top point right there, we'll call this point number 1. Okay, at point number 1, the distance, that constant right there, that constant distance is 2h. Okay, now let's look at a second point. Let's look at this point like right here, right, one of the vertices in this case. And we look at that distance again, okay, so we'd start here, we'd start at this vertex, and we'd go all the way over to this little, to that vertex, right? So from this vertex, sorry, from that focus, from this focus to that vertex is 2c, so this is for number 2 here, and this is going to equal, that distance was 2c plus a little bit. Okay, plus this little bit. When I say little bit, I mean this little bit right here. Okay, the little bit that goes from there to there. Okay, that little bit. So, oh, how can I undo that? I don't know how to undo. Wait, undo. Yikes. There's the undo button. Okay, I don't know what the undo button is, so I'm just gonna put that back. I'm gonna try to put that back in there. I hit there. Oh my god, that's such a good job actually. Okay. So anyway, like we were saying, we had 2c plus a little bit, and that got us to this vertex. Now to get back from that vertex to the other focus, I have to go another little bit here. So 2c plus little bit plus little bit is gonna equal 2h from example number 1, from situation number 1. Okay, that's point 2 right there. Now we don't want to just settle for a little bit. We can say that this little bit, this distance right here, is equal to a, because a, remember, a was, I'm just going to draw this lower. A was from here to the end. It was from the center to the end, on the major axis, and then c was from the focus, which was right there, right? So C was blue. My bad. C, and that's gonna go there. So this distance right here, okay, that distance right there would just be a minus c. Okay, that distance is a minus c. So that little bit is a minus c. So instead, let's say that 2h is equal to 2c, then plus 2 times that a minus c thing we just found. A minus c. Okay, and so we can see then that 2c is equal to 2c, sorry, plus 2a minus 2c, which is just the 2c's are going to cancel. 2h is equal to 2a. Okay, so this might not seem significant, but what it tells us is that that constant, that distance, the sum of those two distances, so in this, like in this example right here, the distance from there to there plus the distance from there to there is 2a. And this is pretty nice. From this we can generate, like if we say that this is a now, right? Because that distance is also a, and I wanted to know c. Well, I can use a right triangle, this right triangle right here. I know I'm drawing all over this ellipse, and I'm actually not doing a pretty bad job of it, but it tells me that if I wanted to, I could say that b squared, and this is how we define the ellipse. Don't get this confused with the Pythagorean theorem, because that's not what it is, even though that is what we're doing here. It's just not the same a, b, and c. So we get this here, but we want to know what c is. Not we already know what a and b are. They're the length from the center to the major axis. Sorry, the length from the center to the vertices and the co-vertices. So if I wanted to solve for c, I would get that c squared is equal to a squared minus b squared. Now this is true for horizontally oriented ellipses, and so it isn't true for vertically oriented ellipses where the b value would be greater than the a value. And so to fix that, we just make this an absolute value, and having that lets us have both situations at the same time. So the two equations I'm going to put on the next slide here, the two equations that we need, I don't know I have the same graph over here, but we had this one, that c squared is equal to the absolute value of a squared minus b squared. Okay, And then the standard form of the conic form of an ellipse, or sometimes they call this HK form, is x minus h, okay, quantity squared, divided by a squared plus y minus k, quantity squared, divided by b squared equals 1. So these two equations right here, they are going to help us do all of these sorts of problems that have to do with ellipses. Now, the one thing to note is if the a value, the value that's in the denominator of the x term, if that value is larger than the b value, so for example, if a is greater than b, then we're going to have an ellipse that was similar to the one that we saw previously. It's going to be like a horizontally oriented ellipse. If a is less than b, or if b is greater than a, we're going to have a vertically oriented ellipse. Okay, so that's something to keep in mind, and it's kind of a quick way to make sure you're doing a problem right. If you see your equation in HK form and it doesn't line up to what the orientation you think it should, then like something's wrong. Okay, so here's a problem here. Now, this is an ellipse. This is an ellipse. It's been given to us in a strange form. This is not the HK form we were used to. When we have that form, it's really easy to pull information off of it and then graph it. So what we're going to want here, what we're ultimately going to want, is to list the coordinates of the center, the foci, and the vertices, not the co-vertices, but the vertices of this ellipse, and then try to attempt to graph it, sketch a graph of it on the graph there. So first step though is going to be, we're going to need to change this equation into the form that we're more comfortable with pulling the information off of, and to do so we have to complete the square. And we actually, for this problem, have to complete the square twice because we're going to have two perfect square trinomials that we're trying to come up with here. So here's what we do. We're going to look at the x terms here, and we're going to say x squared plus 6x, and then we're going to leave a little space. And from the y terms, we're going to factor out a 9, because in order to complete the square, this coefficient needs to be 1. So we're going to pull the 9 out, and we're going to be left with y squared minus 4y, leave a little bit of space, and then that's going to equal negative 36. So I move the 36 over right there. Now you have to think, what do you have to add to x squared plus 6x to make and you have a third term there to make it a perfect square trinomial? Well, you look at the 6, so you divide it by 2 and square it. So 6 divided by 2 is 3, squared is 9. So I need to add 9 to the left side of the equation. If I add 9 to the left side equation, I need to add 9 to the right side of the equation. Okay, now we can look inside the parentheses, and we see the y squared minus 4y plus something. We need a plus some, we need to add something in there to make that a perfect square trinomial. By the same thinking, it would just be 2. Okay, so sorry, there's 2 squared, it should be 4. I don't know what I'm doing. 4. And when we put that 4 in there, what we really did was everything inside that parentheses is being multiplied by 9. So what we really did to the left side of the equation is we increased the value of it by 36, positive 36. So we need to also subtract. Need to add 36 to the other side. So I'm going to add 36 over here. Okay, so what that leaves us with, after we clean up the left side, this is going to be x plus 3, okay, quantity squared. And then we're going to add, we have plus 9, and then that's a y minus 2 quantity squared. And that equals, those 36's cancel on the right side, we're just left with 9. The last step would be divide both sides by 9, because we want this whole thing to equal 1. We want 1 to be on the right side of this. So when you divide this all by 9, you are left with x plus 3 quantity squared divided by 9 plus y minus 2 quantity squared divided by 1 equals 1. So let's pull this information off here. First of all, the center is super easy to find now, because if we refer back to our standard form of our conic form of an ellipse, we had, remember, it was x minus h quantity squared divided by a squared plus y minus k quantity squared divided by b squared equals 1. So hk was the center, right? Hk is the center. So for this problem, then HK is just going to be negative 3, 2. So the center's at negative 3, 2. Okay, the next thing we can do is find C. So we already know, actually we can find the vertices right away. The vertices are going to be A in either direction of the center. And what we said in the previous slide was that if this term is, if this A is, this is A squared, if A squared and this is B squared, if A squared is greater than B squared, or if A is greater than B, same thing, we'll have a horizontally oriented ellipse. And so just a quick sketch over here on the right. If our center is at negative 3, 2, it's right here. And that means that our A value is 3, so we'd have a vertex right there. And we'd have a vertex right here. Okay. Sorry, I did that wrong. Negative 3, negative 2 I put. So we have a vertex there and there. We would not have anything down here. That's the wrong spot. And so this graph, this sketch, this ellipse is going to do something like that. Oh, I did not do that well at all. It's going to do something like that. Okay. So that means this is a vertex and this is a vertex. And that distance right there, A, is 3. So what we can do is look at this when we want to know the vertices. We can say, if we wanted to like generally say what they were, it would be for a left and right or a horizontally oriented ellipse. We could say that it's H and then plus or minus A, comma K. To see what that does, like we take our negative 3 and we add 3 to it, and we'd have 0, and we take a negative 3, subtract 3 to it, we'd have negative 6, and that would give us the x coordinates of the vertices. So for this problem then, the vertices are going to be at 0, 2, and negative 6, 2. And you can look at the little sketch we did and confirm that. Okay, and then lastly the foci. And the foci are always going to be along the major axis. We can tell from this sketch that the major axis is horizontal in this. And so we can say, similar to how we did with the vertices, that the foci is just going to be, it's going to be H plus or minus C, comma K. Those are going to be the coordinates of the two foci. But we don't know what C is yet, so let's look at that. C, remember, C squared is equal to the absolute value of A squared minus B squared. I don't know what these little strings are on the letters. I don't know why that's happening. So C squared then is going to be the absolute value of A squared, which was 9, minus B squared, which was 1. So C squared is equal to 8. So C is going to be, when we take the square root of both sides, we get 2 root 2. Okay, so C is 2 root 2. And then if I want to write what the coordinates of the foci are, I would say that it's negative 3 plus 2 root 2, comma 2. And negative 3 minus 2 root 2, comma 2. And so now all we really need to do is transfer all that information onto the graph and do our best job of sketching it. So let's see this. So we're going to put the center, we'll put the center in red at negative 3, 2. We already had it on there before, but that's fine. Okay, we'll put the vertices at where they go, which is 0, 2, and negative 6, 2, right there. We know that B is 1 because B squared is 1, so that means B is 1. So technically, we also know that if we go up and down either direction from the vertex, from the center, we'd have the co-vertices. And then the last thing we need to do is put in where the foci are. Now, 2 root 2 is it's like I don't really know what 2 root 2 is. I know root 2 is about 1.4, so 2 times 1.4 is like 2.8. So when it goes negative 3 plus about 2.8, we're almost at 0. So the foci is going to be a focus right here, right near the vertex, and there's going to be a focus right here near the vertex. And then we're just going to sketch in we'll sketch in the actual ellipse. And so we should have something like this. I had to do that in purple. I don't know what happened. Fix it. Yeah, something like that. Okay. Now, on the graph, we'd probably want to label that the foci are where they are. So this was the foci, what was that, negative 3 plus 2 root 2, comma 2. And then this was the focus that was at negative 3 minus 2 root 2 over 2, comma 2. And that'd be it. Now the eccentricity, the thing we mentioned before, is basically it has to do with C. How far from the center is the focus? You can imagine if the focus was closer to the center, we'd have something that resembles much more of a circle. In fact, if an ellipse has 0 eccentricity, it's called a circle. The larger the eccentricity, the more like stretched out the ellipse is. Okay, that's the end of the first video. It's already been 25 minutes. And then we'll go to make a second video.